Maybe for our listeners who aren't aware of what the standard model of particle physics is, could you explain it? I mean, it's hard to explain the whole thing, but give a basic rundown of.
Well, it's really kind of our best understanding, really, of kind of fundamental physics, ignoring for the moment gravity. And so, and it basically says that there's kind of three kinds of forces. There's the electromagnetic force, the weak force, and the strong force. And they all, the really beautiful thing about it is you can write them all in terms of the same kind of mathematical structure. The structure is called based on what's called gauge symmetry. Mm-hmm. And so you just have, anyway, you have slightly different groups for these three things, but the way forces work is kind of uniform between these. And that's part of it. The other part of it is the theory of kind of matter fields, which are based upon spinor fields and the Dirac equation. And this, so this is an idea that goes back to the early days of quantum mechanics, and Dirac who wrote down kind of the first kind of relativistic theory that works. And there's the Dirac equation is also this kind of amazing piece of it has these amazing mathematical implications, but it kind of was kind of discovered in physics in some sense. So you've got matter fields described by the Dirac equation, you've got forces described by gauge fields and gauge symmetry, and there's this one, probably the most mysterious aspect of it is the so-called Higgs particle, that it's some kind of field responsible for a phenomenon that the gauge symmetries, get in some sense broken and don't work in the way you would expect. The vacuum, normally when you have symmetries, you assume that the vacuum state, the state of the world, which is lowest energy, there's nothing there, that's invariant under all the symmetry transformations. Well, it's not true. The Higgs field makes that not true, that the SU2 gauge transformations kind of change the nature of the vacuum.